Okay. Hopefully that's working. So, I left you all last time with the challenge of seeing whether you could find a lambda calculus term that reduces to itself. So did anyone think about that or come up with one? So I'm going to call this term, I'm going to give it the name copy. So for example, if I say, copy X, or copy, let's say X, copy Z, right, this reduces to, well, this is defined as lambda X, X, X applied to Z, which reduces to ZZ. Right, so I started with one Z and I ended up with two applied to each other. So what happens if I copy copy? So that's, I can just separate that out. What does that reduce to? Yeah. So I have a lambda applied to something. So this something is going to be this x. So I get rid of this lambda and I just have this something applied to itself. There you go. So that is a term that reduces to itself. Right? And usually this term is called capital omega. It's the simplest possible example of a term whose reduction never terminates. Right? And it's all because it's not so much that it's recursive, right? It's not defined in terms of itself. But the fact that we can take some thing and kind of duplicate it. Right? If you have a duplication machine and you use it to duplicate a duplication machine, then you have two duplication machines again. So this is really just a curiosity, this omega. It's not actually useful for anything other than demonstrating that things in the lambda calculus might not stop running. And in fact, so just a little bit of a historical tidbit. So remember that Alonzo Church came up with a lambda calculus. He was trying to come up with an alternative foundation for mathematics. He said, forget this set theory stuff. Maybe we can make a foundation for mathematics that is based on the idea of functions instead of on sets. And so he defined this lambda calculus thing, and it had a whole bunch of extra features in it. I think his original version, it even had natural numbers built in. You didn't have to encode them like this. And it had a bunch of extra bells and whistles. But this was the very early 30s, maybe 31 or 32. And then a few years later, 1935, his PhD students, Barclay Rosser and Stephen Cleaney, found this. And we'll talk more later about why. But basically, if you can do this, this means that the whole system falls apart as you can kind of use this to prove anything you want. If you're trying to use it as a logical foundation for mathematics, here's an intuitive idea why. And we'll see in more detail why over the next few weeks. But right? It's like if I promise to prove something for you, right? You could say, all right, give me that proof. And I say, I promise I will, come back tomorrow. Right? Then you come back tomorrow, and I'm like, sure, I promise I will, come back tomorrow. And I keep telling you to come back tomorrow, and I'm never actually going to prove it. Right? So the problem is it's hard to distinguish, like, maybe I'm just thinking really hard, and like if you keep coming back at 5 days from now, I'm going to prove it. And so you can't like reject me out of hand because like you have no reason necessarily to distrust me in the first place. But so you can't tell the difference between a supposed proof that will actually like finish and give you a proof, or a supposed proof that will just run forever and never actually do what you want. So that's intuitively why this breaks lambda calculus as a foundation for mathematics. We're going to come back to that, but first let's think about how to make this into something slightly more useful so we can actually do useful recursion in the lambda calculus. Okay. So we need, right, we want to define a term y such that, and so this is aka fix. We call it fix in Haskell, usually called the y combinator in lambda calculus. And there's a well-known startup like incubator called Y Combinator, which is named for this thing. So we need a term y such that yf reduces to f yf. Right? That's just how we defined fix in Haskell. So if I just say, if I just chose y to be copy, for example, then I just get ff. So that's not good enough, right? I need f yf. Another way to look at it, right, is that I could say, well, if I take like I want to copy something. I want to copy the yf, so I end up with the same thing, but I want an extra f on the front. It's been a long time since I've thought about this. I have the answer written down here, but it feels intellectually dishonest to just write the answer up here and be like, there, it works.
I mean, if you want.
Yeah, I mean, I agree. I may get there in a couple minutes, but maybe here's the way to think about it. So remember, in order to get this term that kind of reduced to itself, we had just like the same term copied twice, and it sort of made a copy of itself. And so we could say, right, what if y is equal to, there's some term c such that y is c applied to itself, right? Then we need cc applied to f. Reduces to f of cc applied to f. Does that help? No, that doesn't help. I didn't do that right. Okay, I'm just going to write the answer up here, and then we'll convince ourselves that it works. let's convince ourselves that this works, right? So if I do yf, right, then, well, I'm applying it to f, and so the f becomes this argument here, also conveniently called f. So this becomes lambda x f x, lambda x f x. Now, what does that reduce to? So here I've got this lambda applied to this thing. So I'm going to take this argument, and it becomes this x. So I now am going to stick that in for x. Right. So I get f applied to this thing 2 times. Right, and this thing here that's inside the parentheses, that's exactly what yf is. Right. Or, well, yf would reduce to this, I guess, technically. So, right, before, like the normal copy thing, I didn't have this f here. I just had lambda x, 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 lambda x, x, x. Putting this extra f here means that every time I apply this one time, I get an extra f on the outside, and then the x, x, I get like the 2 things copied again. Every time I reduce, I'm going to get another f on the outside. You have a question?
I was just thinking through how this is working.
Oh, yeah. Maybe I should even do does that help? Yeah, David.
See the recursive aspect of it, but I don't understand how it just goes and becomes f of y of x.
It doesn't. I mean, the point is it's equivalent. You're right, yf is not literally this. Yf is like lambda f dot this thing applied to f. But if you reduce that one step, the f gets substituted in here and you end up with this thing. So it is equivalent to yf, which is good enough.
That's a question.
Yeah.
The term that you have in here,
Mm-hmm.
it looks like it's got to y only, not yf. You see what I mean? Like,
No, it's y has an extra lambda f on the front. Right, so if I do yf, the f is the argument that gets substituted for this, and then I'm just left with that. Okay, so let's see if. Sorry, I'm like, I should have done the other word. That's okay. We'll recode it. this in. Okay, so I'm going to find y as lambda f, lambda x, f, x, x, lambda x, f, x, x. Okay, and let's do, okay, we'll just make a few numbers. And then we'll do plus. I'm trying to. Oops, I don't wanna do that. Oh, it's okay. That's got weird. Okay, let's try this. Okay, I'm just trying to come up with a good example of using the Y Combinator, where we. Okay, yeah. Let's just try to write down like the classic SomeToriel function, right? So you can write SomeToriel. You don't need fix. You can just take a number n and you can just use n to iterate something n times. But let's not do it that way. Let's do it using the Y Combinator to see if I can do that. And some things you don't need the Y Combinator for. Some things that you would normally use recursion for in Haskell, you can get away with just like using the fold for a natural number or a list or something. But there's some things that you absolutely do need it for. So SomeToriel 1 is going to be, well, it takes a natural number n, and it says, oh, we need an if 0, don't we? So if 0, or I'll write it as if 0. n lambda x dot false true. I guess I need false and true, don't I? Okay, so true is lambda f dot t, false is t lambda f dot f. Okay, so how does SomeToriel work? It says if n is 0, then we return 0. So if 0 n, then we're going to return 0. Else, we're going to return plus n. Oh, right. I need to take an extra like recursive argument, right? This is just like, yeah. R. Oh no, I need -1. Drat. Okay. Yeah, actually, it's right. It's maybe harder to do it this way then. Fine. So, pair x, lambda, f, x, y. No. Okay, we're just going to say p true, p false, and then next equals lambda p. P a b pair of b. No. That is lambda n, and we're almost there. N of next pair 0, 0. Okay. I think that should work. Okay. R pred n. So let's load this up. Okay, let's make sure, like if I say pred of 3. Oh. Some of you are running into this. If this happens, like, notice I got like an S and then it just seems like there's some lambdas here that aren't doing anything. It's just because it's not running for enough steps. So by default, it'll run for 100 steps, but you can change how many steps it's going to run by. You put a number and a colon, and then, wait a minute, oh. Uh-oh, I think I have a bug. Anyone see my bug?
I think you're just taking the whole pair instead of just the first of the pair.
Oh, yes, thank you. You're right. So pred should be first of that. Thank you. That's better. All right. So I should be able to say I can get my normal recursive SomeToriel function by applying the Y Combinator, which is the same as Haskell fix, to SomeToriel 1. Right, SomeToriel 1 is not recursive. It just takes this extra function parameter R and calls that where it would like to be recursive. And then fix, or Y, ties the knot, as it were. So SomeToriel, well, let's try with something really simple to start. 0. Yep, it's 0. Very complicated way to write 0. 1 is 1. 2. I'm going to start running out of gas here, so yeah. This should be 3, right? It's 3. 3. 1, 2, 3, 4, 5, 6. Looks like it's working, right? 4. Yeah, 1,000 is not enough gas for 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, okay, so that works. Anyway, so hopefully, here's the point. What's the point of all this? Hopefully you are now convinced that basically any program you can imagine writing, you can encode in lambda calculus. Any data type that you want, you can write down a fold for it and you can encode it using a church encoding. We have the Y Combinator, so we can do arbitrary recursion. We have numbers, so we can do loops and stuff. Well, and in fact, if you just have recursion, it turns out, Haskell doesn't have loops, right? But it can do so. So it is in fact Turing complete, which was proved by Turing in 1936 or 7. After this these grad students found out that you could do recursion in the lambda calculus, he was like, oh, well then probably they're equivalent, and he sat down and proved it. Questions? Okay, so the story didn't stop there, obviously, because we're talking about the lambda calculus now, right? If the lambda calculus had just been a horrible failure, in 1935, and then nothing else ever happened, then we wouldn't be talking about it. So the next interesting thing that happened was that several people, and I'm forgetting who actually, but I can look that up later, said, all right, so you can do recursion, arbitrary recursion in the lambda calculus, but only because you're doing ridiculous things like applying a thing to itself, which doesn't make any sense. Like, you shouldn't be able to have a function and apply it to itself. And so they come up with something called the simply typed lambda calculus, which it turns out is not Turing complete, because you can't do arbitrary recursion in it. But you can do a lot of things that you want to do, and it has the very nice property that any term you could possibly write down, it will stop reducing after a finite number of steps. So every program or every term you can write down in the simply typed lambda calculus terminates. And basically, the way you do that is by ruling out some bad terms that you don't want using a type system. And so, let me give you my sort of general take on what a type system is. So you've got some programming language, and here's the space of all possible programs you could write in your programming language, right? And so actually, even before you get to here, there's some things you could write down that aren't even, like, there are syntax errors, right? I'm not talking about those. So those get kind of ruled out at an earlier stage. But it's not even worth calling them programs. They're not programs, they're just like strings, right? So something that is a valid, syntactically valid program, and there's some programs. Well, over here we'll say like good programs, and over here we'll say like bad programs. And what do I mean by bad programs? Well, it depends. It depends on what you want, right? So, for example, maybe a bad program like crashes, or it it leaks secrets, or maybe a bad program is a program that runs forever. And I'm not saying that these things are always bad. These are like examples of things that you might consider bad in a certain context. I mean, sometimes we like that we can have programs that run forever because we can't necessarily a priori rule out, or like tell the difference if we just like the power. Sometimes we want the ability to crash because we want to write a program that's like super close to the bare metal, and we need the control, and so we don't necessarily rule out possibility. But anyway, there's some set of good programs, right, that don't do bad things. Okay. There's some set of bad programs. And I should make this line kind of blurry. the abyss. If I could draw dragons, I would draw some dragons in here. So there's a theorem called Rice's theorem that, oversimplified, says any interesting property of programs is undecidable. So like any non-trivial property you might care about a program, there is no program that can reliably tell the difference between good and bad programs along that property. So the most famous example of this is the halting problem that says the property I care about is, does a program stop eventually or not? And so, Turing's famous theorem is you can't tell. There is no machine you can make that can reliably tell apart terminating and non-terminating programs. But any property you like, does this program ever print the number 3? Undecided. Does this program ever leak secrets that it shouldn't leak? Undecidable. Does this program, I don't know, pick whatever property you want. There's always going to be programs where you can't tell. Right? So, so we definitely can't hope for some system that will let us write all the good programs we run and rule out all the bad programs. It's not possible. Right? So what we do this is type systems. One way we can do this, we have various ways of carving out some conservative subset of the good programs. So type systems is one way that we usually do this. I mean, there's other ways, but right. And you design a type system so that if the type system says your program is good, then it's definitely good. Right. But because of Rice's theorem, there's always going to be these programs over here that actually are good, but your type system says nope, I don't accept that. Right. A lot of research in type systems is oh, maybe we can if we do some really complicated thing, we can kind of push this out a little bit. And there's a few programs that we couldn't, the type system rejected before, and now we can write them. But you can't ever match this boundary. You're always just pushing out a little bit. So, in the historical context here, right, is that the simply typed lambda calculus was designed as a type system to rule out programs that run forever. Okay. But there's lots of programs that don't run forever that the simply typed lambda calculus says no, that's not valid. But that's the price we pay for having some kind of, we have to have some kind of conservative approximation. That's the only way to do it. Okay, so simply lambda calculus, which is also very standardly abbreviated STLC, and you'll understand why I always get confused about this now, because we have the SLTC, and I spent my all grad school thinking of the STLC, and now I'm just getting confused. But anyway, so we're gonna write down. We'll start at least today. See how this works. So if so goal, come up with a set of types and a way or rules for assigning types to some terms of the lambda calculus. Right, some terms, because the whole point is to rule out some bad terms that we don't like, and to allow some ones that we know are good. And sort of the original goal of this was to rule out non-termination. But it turns out that it has ramifications far beyond that. So, well, let's define our types. So we'll call our types. Use some Greek letters for our types, because why not? And everything in the lambda calculus is a function, right? So we want some kind of function type. However, if I just have this is not a very good definition, because now this says, oh, a type is anything that looks like a type, arrow, a type.
That makes sense.
What? That makes
Just
sense?
leave it at that. No problem.
Okay, right. What's the problem with it? Can you write down a type?
I mean, if a type is a thing that has a type that goes to a type, then there's never going to be like a fundamental way to bear, and it's
That's
just
right.
going to be recursive.
That's right. The only things would be infinite, like I just infinitely many arrows. So we're just going to add like. I'm just going to use like some capital letters to represent base types. It could really be kind of anything we want. Think of it as like int, bool, char. But we're not going to put any of that like stuff for dealing with these types in the language right now. But they're just there so that we can write down. Right, so now we can have types like A arrow A, or we'll just B by itself would be a type. A arrow, B arrow, C arrow, D, whatever. Right? And then, so these are our types. And we're going to write down. What did I call? Oh yeah. Put it. So we're going to define some rules for when we can say that a certain term has a certain type. So if I come and say to you, so remember, terms can be three things: variables, lambdas, or an application. So we have to give a rule, at least one rule for each of those things. Now, if I just came to you and said, okay, so we're talking about Haskell now. And if I said, Innocent, what's the type of X? What would you tell me?
Can you create a variable?
What was that?
A variable? Because you say
It is a variable. What is its type?
it's a thing. I don't know.
Like int, char, like what?
Okay.
What is it?
It's a int, for example.
Are you sure?
I don't know. It could be a boolean,
Yeah, right.
It could be a double.
That's right. Okay, the point is, right, you don't know.
Okay.
I mean, maybe the correct answer is, what is x? If I say, what's the type of x? You're like, I don't know, what's x? Right? So, once again, so this is, we go back to thinking about the rules we made for propositional logic. Right? We have to have, if we're going to give a type to a variable, we have to have maybe some assumptions that say, oh, I'm assuming that the variable x has type int. And then if someone asks me what's the type of x, I say, oh, it has type int, because currently I'm assuming it has type int. We'll see we have the same problem for lambdas. So we're going to add, similarly to the predicate logic, we're going to have these contexts. So a context is it's either empty. Right, before with the predicate logic we just said, well, we're just assuming some proposition, but I'm not assuming propositions now, I'm assuming like that certain variables have certain types. Right, so these are our context, our assumptions, and this is the empty context. And this says x has type 5. So in general, right, a context looks like a big list of variables with their types. So in that case, right, under what conditions can I say that a certain variable has a certain type? What do you think I should put above the line? And this kind of goes back to the question that I was asking Innocent.
What is that thing? What is x?
What is it? That's what you're asking?
Yes.
Yeah, so under, are you asking me, or you're saying the answer to what goes above
You
the line?
told me the best answer
Right.
to the question asked me was
Yeah.
like, I need to ask you what x is.
That's right, exactly. And where we record that is in our context gamma, right? Gamma is where we say, here's what we're assuming about some variables. Okay. So right. The point is x had better be in there, and the context should say that it has type 5. Okay, so if I see that assumption in my context somewhere, then I can say, okay, I'm going to assign it that type. Let's do, so we have three, right? We have an application rule. So what do you think? And again, just think, use your intuition that you built up with Haskell to answer this question. If I want to say that an application, T1 applied to the argument T2, has type phi, what should be true about T1 and T2 for me to be able to say that?
Each one should also be of type 5. So their combination should be.
So in Haskell, if I said T has type int and X has type int, then T applied to X has type int?
Yes, supposedly.
Okay, I don't think so.
You can divide the two ints and you get a double. So
What was that?
it's possible to have like two ints, and if you divide them, you
Oh,
get
you're
a
dividing
double.
them. Okay, but we're not dividing them. We're just applying. This is a function, and I'm applying it to this argument. Right? I'm just putting a space in between them. Anyone else? Yeah, Andrew.
Wouldn't it have to match the type of the function?
So, yeah. So for T1, you mean?
Mm-hmm. Like, wouldn't phi have to be the same type as T1?
Not the same type as T1. I agree. There's something about phi has to match the type of T1 somehow. Right, but it's not literally the same type. Again, in Haskell, if I said, oh, I've got a T1 that's type int, if I apply it to something, that doesn't make any sense. I'm not going to get an int.
T1 has to return 5.
It has to return phi, right. So it has to be a function. Okay, what else can I say? What does the input type of T1 have to be?
T2. Oh, the type of T2.
Yeah, it has to match the type of T2, right? Okay, so we'll call it something. It doesn't have to be the same as this type, right? It could be a different type. So we'll say psi or phi. Yep, exactly. So this is just saying, look, T1 had better be a function type, have a function type, and the type of T2 needs to match the declared input type of T1. And then if that's the case, then the type of this whole application is just whatever the output type of T1 is. Should we try? Let's see. Only like a minute, but. So, what kind of type should a lambda have? Oh yeah, good.
The type of its output, which in this case is T.
T is not a type. Or you mean whatever the type of T is?
Yes, because that's the output of the lambda.
Okay. There's definitely something, it's going to be related to the type of T. I agree. The output type has to agree with that. All right, we'll come back to this on Friday. You can maybe see if you can figure out a good way to write down this rule. Yep, see you on Friday. And we will read those chapters of the book. We'll talk about it.